In this video, we're going to take a look at how we implement a deletion in our red-black tree. To help us with our deletion, we're going to implement a few helper functions first, the first of which being a function called transplant. And what transplant does is it basically replaces the node u with the node v. There's a few different rules that we'll need in order to do this, right? So the first is to check if u has a parent. If it doesn't have a parent, then it must be the root, which means that the root now becomes the thing that we're replacing u with, which is v. Otherwise, if it does have a parent, then we check if u is the value that's on the left-hand side of the parent. If it is, then we set the left equal to v. Otherwise, we set the right equal to v. And then finally, what we do is we just set v's parent equals to u's parent, and we're done. So what this is really doing, like I said, is replacing u with v, so it's a transplant. So this is really important because if you remember in our deletion with our binary search tree, what we were essentially doing was we were going to be replacing the node that we're deleting with something else, right? So in the case of where it has like no children, or it has, well, with no children, we replace it with nil. With one child, we replace it with the one child that exists. With the case where we have two children, we replaced it with the in-order successor of the right-hand side of that particular node, right? So this is basically going to allow us to do that replacement in a bit of an easier way, since there's a few steps required for that in this type of deletion, right? The second thing we need to be able to do is find the node that we're actually looking to delete, which I'm going to do using what we would call the search function. The search function is basically going to look for the value, and it's going to return it back to whoever called it, right? So basically the main process for this is we check to see if the current is equal to self.nil. If it is, we return none, basically meaning that we didn't find the value. Otherwise, if the current value is equal to the value that we're searching for, we're going to return current. Notice that we're returning the actual node itself. The reason that we're returning the actual node is because basically what we do with our deletion, right, is we search for the value that we're trying to delete, then we take that node and do something with it. So this is finding the node, and then the deletion is actually deleting the node itself, right? If it's less, then we have to do an iteration, and we're going to do that recursively. We're going to go to the right-hand side with the value that we're searching for. And then the main else here is going to return basically a similar type of situation. We're going to do a search aux with current.left and the value that we're searching for. I just noticed that I forgot the return here, so let's place that back. And then what we need here is we need just like the main search function, which is the one that's going to kick off our recursive calls. So we're going to search for a particular value. We are then going to return self.search auxiliary with the value that we're searching for, starting at the root of the tree itself. Great. So from here, we're going to actually do our delete, right? So the delete process looks like this. Very first thing we need to do, find the value we want to delete, right? So we're going to search for that value using our search function. That'll give us back the node that contains the value that we're looking to remove. If that node is not none, right? So if the node actually exists, then we can proceed with deleting it. If it doesn't exist, then we don't want to try to delete it, right? Since it's not actually there. And what we're generally going to do is we're going to set a variable equal to that node to remove. So we'll create like a holder for it. And I'm also going to hold on to the original color of the node to keep track of this information. So we'll need it to determine if we need to do a fix at all. What I'm going to do from here is I'm going to say if the left is equal to self.nil, then basically x is our other variable here that we're going to keep track of. And I'm going to set it to the node to remove dot right. So the right-hand side of the node that we're trying to remove. And then from here, what I'm going to do is a transplant of node to remove and node to remove dot right. Right? Since if there isn't a left-hand side child, we just replace the node with its right-hand side child. And then similarly, we have the same sort of process if the node to remove dot right equals self.nil. We basically do the same sort of thing. We're going to keep track of the left-hand side of the node that we're removing, and then we're going to do a transplant of node to remove dot left. I didn't really explain it too well. The reason why I want to keep track of this information is because later on I'm going to need to know basically what we've replaced the node with, right? So you see here basically that right is the thing that's going to end up replacing the node that we're deleting. We want to keep track of that for later down the line when we're doing fixes to the actual node itself. Now the final case here we know is if we have both children, right? If we have both children, I need to find the one to remove, right? So I'll go ahead and go to the right-hand side, and then I'm going to do my iteration to say, well, I haven't reached a nil, and the value to the left does not equal self.nil. And what we do here is we basically say temp equals temp.left. And that takes us to the in-order successor, right? The next largest value closest to the one that we're removing. And then basically I'm going to set y equal to that value. And again, I'm going to set the original color equal to this color here. And then my x is going to be equal to y dot right. So it's going to get us saving that value that we're using. And then basically what I need to do here is a quick check. I want to check to see if y does not equal the node to remove dot right. If this is the case, what we're going to do is we're going to transplant y with y dot right. And then from here, we set y dot right equal to the node to remove dot right. And then we just update the parent to point to y. On the other case here, it's a bit easier. All we do is we set the parent of x equal to y. And then finally, the last piece that we need to do here, basically in the general case here, is to say self.transplant of the node to remove and y. And then we just update each of these pieces. So this becomes node to remove dot left, y dot left dot parent is equal to y, and then y dot color, we're just going to have it inherit the node to remove's color. And then from here, we have to potentially do some different fixes, right? So basically, we want to check to see if we need to actually do a fix. And the case where we need to do a fix is if the original color is black. Basically, if we remove a black node, we have situations where we may have a misbalance of the actual number of black nodes or something similar, right? So in this case, we want to actually do fixes on the deletion itself. And these delete fixes look really similar to the insertion fixes, right? So basically what ends up happening here is we're going to go ahead and iterate through doing iterative fixes as we move through the tree. The condition for the while is basically if the node doesn't equal to the root and the node color is black. So if we have black nodes, we want to do fixes potentially to them. And we have a pretty similar setup to our insertion. So we start by checking if the node is on the left-hand side of the parent, right? If the node is on the left-hand side of the parent, what we're going to do is the following. I'm going to store the right-hand side of the parent, and then we're going to do some comparisons with it. So I'm going to check to see if the color of the right-hand side is equal to red. If it is equal to red, then we're going to do a recolor. We're going to change the color to black. We're then going to change the parent color to red. And then we're going to do a rotation on the parent itself. So we do a left rotation on the parent. And then we set W equal to the parent.right. So this is our first case of correction here, right? The second case of correction is going to be if the left color is black and the right color is black. So both the left and right are black. So it's kind of like the counter to the actual setup of our insert where we're looking at both being red. In this case, we're looking at both being black. In this case, we simply update the color to be red and we set the node equal to node.parent and continue iterating from here. Now there is an else case on this, so if one of them is not black, essentially. In this case here, what we end up doing is we check which one. So I'm going to check if the right color is black. If it is, then we're going to set the left color also to be black. We're going to set W's color to be red, and then I'm going to do a rotation on that. So I'm going to rotate to the right with the node W. The outside of this is basically going to update the actual color to be matching of the parent color. Where they're going to set the node's parent color to be black. We're going to set W's color, or W's right's color to be black. And then we do one final rotation through with the node.parent. Finally, from here, we set the node equal to self.root. When we actually do that, you'll see that basically instead of this condition, because node does not equal self.root, once that gets set to root, this will essentially exit out. So this is sort of the last step of our iteration, right? Now from here, basically what happens is the symmetry takes over, right? So we take all of this, and we're essentially just going to place this into the else. So on the else here, basically what we're saying is if the node isn't to the left of the parent, so it's to the right of the parent, right? In this situation, again, like I said, all of the lefts change to rights, all the rights change to lefts, and we have the exact same setup, right? So again, as I mentioned before, it's really just a matter of, remembering one of the sets of cases, and then from here, we just update our colors based on it, right? So left becomes right, right becomes left, and everything is okay. So this becomes left, this becomes right, this becomes a left rotate, and we could just continue on from there. All of these look good. This becomes left, this becomes a right rotate, and we are done from there. Now, one final piece that needs to happen essentially here is we need to update the node color to be black. And generally this is happening as we're exiting out of the actual while loop itself. Now, the reasoning behind this is essentially because of the actual root property needing to be null. By the end of this, basically the node is going to be equal to the actual root itself. So there's basically two different cases that we can really take here. So we can either update node or we can update root. I think it makes most sense just to write it as self.root.color equals black, just to make sure that that coloring remains the same. And that gives us our deletion. Let's just try it out and make sure that I haven't broken anything. So I'm going to do a delete of the value 4 as an example, just to try it out. And we'll just take a look and make sure that all the syntax is correct. It doesn't give us any sort of errors. Let's see here. You'll see that the node 4 did end up getting deleted. 2153 is what is left. Now, what if I were to delete the root, which is 2, right? If I do that, do you see I get 3145? We get a new root getting promoted up, and everything is still working. So you can see that we could delete, any sort of node that we want, and we end up with a functional outcome of that. And it looks like we actually do rotations and fixes because the root actually gets updated from that process. With that, I have insertions, deletions, and you've tackled probably the hardest kind of tree structure that we're going to talk about inside of this course, which is the red-black tree. So congratulations on completing this section. This is probably one of the more complex data structures that we'll really talk about in this course. And have a good understanding of how to implement and balance out a binary search tree. So thanks so much for watching this video. I'll see you in the next one.